Okay, so here is my screencast for the MouseTrap grading route, MouseTrap car. And first and foremost, evidence that student built the car. Um, Unfortunately, by the time that I was done making my car, there was nothing else to put on. But I do have this lovely picture of me with my with my box before I started building it, and here's all the wheels that I was considering putting on it. I used actually a yo-yo string for the string to attach to the axle from the MouseTrap car, and it eventually turned this piece of work right here, which unfortunately didn't go far, and it went too fast from where my camera was for a tracker to be able to track it. So instead, I used my good friend Persant's car data, and I just finished working with tracker because the what was it called? The scaling is off for Persant's data, which is right here. Very beautiful data in nice parabolic form. Energy stored in the MouseTrap spring is over here. I was able to take a picture of my calculations over here from using the wheel to find the energy stored within the spring, and this is the graph that I got. Nice linear graph, and to find the energy stored under the spring, you need to find the area under the graph itself. So basically, it's just a triangle and a square, and you multiply that by the constant factor to get your constant, and then use the equation force equals Newton meters over the angle which you have, and then then you add 1 Newton because you have 1 Newton of force, and then you have 7.03 Newtons, so that is the energy stored in my MouseTrap spring. And the position versus time graph, I go back to Persant. The position versus time graph, the maximum position achieved by Persant's car up here is approximately 1,435 meters, but that's not right. I found out that the conversion factor for the MouseTrap car graph, which Persant has right here, is you have to multiply the meters by 0.0036, and that's what I was analyzing Persant's video for, to find the conversion factor, and that approximately comes out to 5.16 meters. So over the course of approximately 3.5 seconds, Persant's MouseTrap car traveled 5.16 meters. The mass of the MouseTrap car I used actually for my MouseTrap car because, I mean, it's still a mass, right? And so my MouseTrap car was able to travel 20 inches, and you plug that into the equation 1/2 k times x squared. And so 20 inches in terms of meters is 0.507 meters, and I squared that, and then you times that by 0.75 joules, which is my spring constant, and divide that by half, and you get k is equal to 0.0963. Hang on one sec, I have a picture of the calculations. Or no, I don't. Okay, that's cool. Okay. Maximum velocity and kinetic energy of the MouseTrap car. We go back to Persant's data, and the approximate maximum velocity here in the velocity versus time graph is here at approximately 1 second, and multiplying that by the conversion factor so that it's not supersonic, it's 2.83 meters per second when you multiply that by the conversion factor and do all the math concerning this graph up here. So that was a challenge, but I was able to get it. And the acceleration of the MouseTrap car, you find, to find this, maximum point here, you need to use stats to find on Logger Pro in order to find the maximum this intersection right here, but where it reaches its highest speed. Now the acceleration of the MouseTrap car during speeding, when it's speeding up, I found out that the acceleration is 1.2 meters per second squared, and the process of slowing down is a little bit less. What's it called? Is a little bit less powerful, and that's 0.64 meters per second squared. So that's the deceleration, or well, it's negative, so negative 0.64 meters per second squared, and that's the deceleration of the Persona's MouseTrap car. And the force diagram of the car during slowing down is right here. Oh, never mind. There's the mass of my MouseTrap car. Okay, so at the beginning, normal force and weight or gravity is the same, and then you have to take into account friction and the force of the spring, or EK, which is transferred into it's E elastic at first, and then it transfers to EK. And so this vector right here is longer than this vector right here, and therefore if you add up the vectors and make a nice little square, you will get this moving against the force of friction, and therefore the energy from EK is greater than friction. During equilibrium, it's the same, and that's only a split second, because I mean the forces of, well, it's almost infinitesimal, but the forces are all the same, and then it's moving at a constant velocity. However, that only happens at like the blink of an eye. So, and the force of deceleration, the force of friction is greater than EK, or the energy that's still stored in the spring. The normal force and the weight is still exactly the same, but just the friction is able to overpower the force of EK. And the Python simulation, I will get on that right now. And the energy flow diagram right here this simulates the car in throughout its 3 stages. And at the very beginning, all energy is stored within the spring, so it's all E-elastic, and E-elastic is at its maximum potential energy, or potential energy is gravity, but E-elastic is at its max. And in this case, for my car, E-elastic is 0.68 joules, and then as it starts to move, E-elastic is transferred into EK, and at its maximum velocity, EK is at its maximum. So at EK, all the energy from the spring is transferred into the car, which is the same amount of energy, because energy is neither created nor destroyed, but it is hindered a little bit by friction. So as friction builds, the EK gradually decreases. And EK is measured by 1/2 mv squared, or not EK, but and then by the time the MouseTrap car stops, friction has overpowered the energy of kinetic force, and thereby you have no movement. The Python simulation will be coming up soon. Thanks for watching, Mr. J. I hope you have an awesome summer.